questions 11 through 10 on the 2003 Grade 12 Euclid Math Contest. A circle with its center on the y-axis intersects the graph of y equals the absolute value of x at the origin O and exactly two other distinct points A and B as shown. Prove that the ratio of the area of the triangle ABO to the area of the circle is always 1 to pi. So here is our graph, a little bit bigger, and let's start labeling as much as we can. I'm going to first join a line from A to B, like that, and then I'm going to start to label the radii first of all. So for example, the circle has a center right here, and if you draw a line from the center to any point, then of course that's the radius. So from O to the center, if that's the radius, we can call the radius having a length of, say, r. Why not, right? So that means that this point right here is 0r. Correct? And in a very similar way, since that is an additional radius, this point right here is 0, 2r, like that. And very similarly, since this is the radius from the center to A, this point right here will be r, like that. Because on the x-axis it's r, and on the y-axis it's r. And in a very similar way, this point B will basically be negative r, like that. Now, just in case you're not convinced, you say, well, how do you know that? How do you know that the point A is RR? I mean, okay, I get it that this point is RR, but just because A is there doesn't mean that is R as well for the X and Y coordinates. Okay, no problem. That's what this is all about, right? It's all about proving. We have to prove. Now, we know that this line from here to here and from there to there is a graph, and that graph is y equals the absolute value of x. And basically what that means is that when you are in this quadrant over here, it's y is equal to x. And what I really meant by that is this quadrant. So when x is greater than 0 or equal to 0. And then when you're over here in that quadrant, the graph is basically y is equal to negative x, like that. Because you can't have any x values that produce a negative y value, because it's the absolute value of x. Absolute values are always positive. So that's basically what this graph means. Now, this graph, the graph of the circle, can we make an equation? And of course you can. The graph of any circle is always x minus h squared plus y minus k squared is equal to the radius squared. Now, what is h and k? Well, that represents the center of the circle. So in our case, our center we labeled as 0r, correct? So our equation becomes x minus 0 all squared plus y minus r all squared is equal to r squared. And that basically means x squared plus y minus r squared is equal to r squared. That's the equation of our circle. Now, we are told that this circle and the graph of y equals the absolute value of x intersect, and they intersect at points A and B. All right, so that basically means that if we just look at this one right here, y equals to x, that means that we can substitute this into here since they intersect. So instead of x squared plus y minus r squared, I can put x, since y is equal to x at this point in particular, only at that point. So x minus r squared is equal to r squared. And then we expand this, and you get x squared plus x squared minus 2xr plus r squared is equal to r squared. And it looks like the r squareds cancel. We get 2x squared, put the minus 2xr on the other side. And then this looks like 2 will cancel, and the x will cancel, and you're just left with x is equal to r. So that basically means that at this point, it is indeed, if you have x and y, it is r, because x is equal to r, we just proved that. And the y coordinate, well, y is equal to x. So there you go. So that is basically, we are proving for sure. Now we get to the part where they're talking about trying to prove that the area of the triangle ABO, so ABO, this triangle, if you were to take its area and compare it to the area of the circle, which is right here, it would basically be 1 over pi. All right, no problem. We can probably do that right here. So what is the area of the triangle? Triangle ABO. Well, it's 1/2 base times height. The base is from here to here, and that would be 2r. And the height is from the center to O, which is r. So therefore, we can now divide by, our other part was the area of the circle. Okay, area of circle. And what's that? Well, area of a circle is just pi r squared, right? And in our case, our radius is just labeled r. So that makes things pretty straightforward for us. So now what do we have here? We've got r squared over pi r squared. The r squareds cancel, and all you're left with is 1 over pi, which is exactly what they have. They're just written it in a different format, 1 colon pi, which is basically the same as 1 over pi. So there you go. We have proven what they've asked. In the diagram, triangle ABC has a right angle at B and a midpoint of M at BC. A circle is drawn using BC as its diameter. P is the point of intersection of the circle with AC. The tangent to the circle at P cuts AB at Q. Prove that QM is parallel to AC. So before I get started with this question, I'd like to teach just 2 brief primers here. The first one is basically known as the inscribed angle conjecture. And it basically states that if you have a circle and you've got a center point in that circle, so right here, and then you choose 2 points on the circle, say A here and B here, like that. And then you draw lines basically from A and B to the center of the circle, like that. And then you draw lines from A and B to another point on the circle, like that. And we'll call that point, say, C. Basically, it states the following, that this angle AOB, if it is, say, 2y, like that, then the angle ACB will be half of that, so it will be y. Okay, so that is called the inscribed angle conjecture, and we will learn to use that later on in the question. And then the second part of my primer involves corresponding angles. And the best way to show corresponding angles is with a diagram. So here you have angles in parallel lines, correct? So in this first one, right here, you've got 2 parallel lines, this one and this one. And they are parallel, and then you've got another line sort of cutting them through like that. These angles that they have drawn in, both being 110, they are equal. That's just the rule. And that rule is known as the rule of corresponding angles. And that's only true if the lines are parallel. So now that we have those two things illustrated, now let's move on with the question. So this figure will be at the heart of our question. We will keep referring to it. So I blew it up here since we will probably need a bigger version of it. And let's take it step by step here. What are we trying to prove first of all? We have to prove that QM, this line right here, is parallel to AC, this line right here. Now, before I start, how do we do that? How do we prove that two lines are parallel? Well, there's a few ways, right? We can prove that they have the same slope, or you can use something I just showed you called corresponding angles. If these two lines, QM and AC, are indeed parallel, then using corresponding angles, this angle should be the same as that angle. This angle right here and that angle right there. Okay? That is what we are going to do in this question. I'm not going to use the slopes are equal. Although if you do it that way, that's more power to you. So the first step is to look at PQ and QB. And notice that both of them are tangent. And since they are tangents, these angles would be right angles. And one of them is already drawn in for you. So I'll draw in the other one right here, like that. Now the second point I want you to pay close attention to is again PQ and QB, but this time understand that they are equal. Why are they equal? Because they are tangents from the same point, namely Q. From Q you drew a line that went to B, it's tangent to the circle, and then you drew another line from Q to P, creating another tangent. And because they are tangents from the same point, they're equal in length. Now the next step, I want you to look at these triangles. QM is going to be common to two triangles. There's this one here with P, and then of course there's the other one with B, like that. Already you're probably seeing that they're identical triangles pretty much, because they both got these right angles, right? They've both got the same side, and they both have radii that join M to one of their vertices. So with that in mind, you will see, hopefully, that the angles will also be the same. And those angles are PQM and angle BQM. So PQM is this angle right here, and BQM is that angle right there. Those are equal. So I'll just label them X and X like that. And in a very similar way, the angles of PMQ and BMQ are also the same. So PMQ is this one, and BMQ is that one right there. So since those are the same, I'll label them Y and Y like that. Now look again at the triangle, either one, for example, this one right here. This is a 90-degree angle, correct? So that basically means that X plus Y, this one and this one, must be equal to 90 when you add them together. Because when you add it to this 90-degree angle, the sum has to be 180. Now, finally, we get to that inscribed angle conjecture. And if you forgot, we'll refresh your memory by looking at it again. Here it is. If you have an angle from 2 points, in this case it was A and B, to the center, and that angle is 2, if you draw another set of lines from A to a point that's on the circle, namely C, that angle will be half of that. So if you use that exact same rule on our diagram here, We have 2 points, B, P and B, like that. We're drawing lines to the center, and they created an angle of 2y. And then you take those same 2 points, P and B, and you draw lines to a point that's on the circle, and this time C. And therefore that angle in there will be half of 2y, which is y. Okay, so that means that angle PCB is equal to y. Now, do you see any other y somewhere? Well, I see a couple, but there's one in particular, angle QMB is equal to y. This one right here, QMB. And at this point, we will employ our corresponding angles. Now, which one are those in this diagram? Those angles are QMB, which is equal to y, and this one right here, the big one, ACB. Angle ACB is also equal to y. And therefore, since they are equal, we have proven, by using corresponding angles, that AC is parallel to QM. And therefore, AC must be parallel to QM. And there you have it. That's the proof. Cyclic quadrilateral ABCD has AB equals AD equals 1. CD is equal to the cos of angle ABC, and cos of angle BAD is negative 1/3. Prove that BC is a diameter of the circumscribed circle. So let's first draw a diagram. So here is a cyclic quadrilateral inside a circle, and I'll label this A, B, C, D. So here's A, B, C, and D. And let's label what other information they give us. AB, they say, is equal to 1. So this is 1 right here. And then AD is also 1. And the cos of ABC, so ABC is this angle right here. Let's call it angle B. So CD is equal to the cos of angle B, like that. And what else do they give us? That the cos of BAD, so that's right here, we'll call that angle A, is equal to negative 1/3. All right. And then I'm going to label a few things here. CD, instead of keep calling it CD, I'll just call it X. And CB, instead of writing that out every single time, I'll write Y. It just makes it a little bit more simpler. Okay, before we get into the proof, let's first digest all this information. So CD is equal to the cosine of this angle right here. Okay, that's fine. Cosine of this angle is negative 1/3. Okay, most likely we will need to use these two pieces of information later on. Now let's get into this definition here. Cyclic quadrilateral. What does that mean? We all know what a quadrilateral is, but what does cyclic mean? It basically means that if you have opposite angles in this diagram, for example, are A and C, this is angle A and this is angle C. In a cyclic quadrilateral, they equal the sum 180. And very similarly, these opposites, B and D, those angles, angle B plus angle D, if you add them, they equal 180. That's what cyclic quadrilateral means. And if you look at each of these, you can sort of manipulate them. So angle C can be 180 minus A. You see what I mean? Or angle D can be 180 minus B, like that. So if you need to, you can do that because it's, perfectly allowable. So now let's look at these guys here. Can we manipulate them in any way? I don't really know at this point, but one thing is for sure, that I would like to get rid of this CD that keeps, coming up. I've labeled it x, so I'm just going to call it x like that. And therefore, we all know, I hope, that if you take 180 minus any angle, like that, and you take the cos, it will be negative x. You can try it. Take a angle, take its cosine, it will be some value. Then take that same angle, subtract it from 180, take its cosine, it will be the negative of that. That's going to help us also because this is cyclic, so there's going to be some 180 minus kind of situation in this question. I can almost guarantee it. Otherwise, I don't see why they would give us a cyclic quadrilateral. And I think anything else that we can do before we proceed? The only other thing I can think of is just, since 180 minus b right here is d, this basically is the same as d. So that means the cos of d is also equal to negative x. All right, so that's it. Now let's move forward with our proof. We are going to use in this question something known as the Law of Cosines. And it's so commonly used that I hope you know it. If you don't, take a minute, review it, and come back. So let's use this, but twice. So first I'm going to use it on triangle ACD, and then I'm going to use it again on triangle ABC. So on triangle ACD, so right here, AC, that triangle right there, we're going to use AC as our primary side. So we got AC squared is equal to 1 squared plus x squared minus 2 times 1 times x and cos of d. And then for triangle ABC, which is this triangle right here, we are going to use law of cosines, but this time again involving AC. And using that, we'll get 1 squared plus y squared minus 2 times 1 times y cos of b. Like that. All right? So let's move this up now and let's work with these two. So we have AC squared is equal to this whole thing, and AC squared is equal to that. So that must mean that this is equal to that. So we can set them equal to each other. 1 plus x squared minus 2x cos d is equal to 1 plus y squared minus 2y cos b. Okay? Now the cos of d and the cos of b, we did figure out, at least in terms of a variable, up here. Cos of d is negative x, and the cos of b is just x. So 1 plus x squared minus 2x cos of d, negative x. 1 plus y squared minus 2y cos of b, which is just x. All right? So it did come in handy. So let's move forward. I think we can put everything on one side. The ones cancel. And let's see, we'll get y squared minus 2yx. This is x squared plus 2x squared, like that. So y squared minus 3x squared minus 2yx is equal to 0. And we can probably factor this. So let me just rearrange it first. Minus 2yx minus 3x squared. And this factors, hopefully, y, 3x, and x minus plus. I believe that is the way you would factor it. So that basically means that y is equal to 3x, or y is equal to negative x. Now y and x represent distances, correct? If you look at the diagram, they represent distances of CB and CD, respectively. So that means that this one doesn't make any sense right here. Y can't be a negative number. You can't have a negative distance. So the only thing that works is y is equal to 3x. All right? So let's go back to that diagram and put that in. Y is equal to 3x, like that. Now, hopefully this is going to help us. Now, at this point, I want you to go back and look at a piece of information that they gave us earlier that we kind of drew over here. This one right here. The cos of A equals negative 1/3. We haven't used that yet, so I'm going to use that now. It's a piece of information given to us. Cos of angle A is equal to negative 1/3. That's this angle right here. Now, if that is true, cos of C we can figure out as well. Why? Because remember, they're cyclic quadrilateral, so A and C, those angles, add up to 180. So basically, angle A is essentially 180 minus C, or angle C is 180 minus A. That's the fundamental property of the cyclic quadrilateral. Then the cos of 180 minus A is the same as the negative of the cos of A. And since the cos of A is negative 1/3, you put that in there like this, and you'll get 1/3 for the cos of C. Okay? So the cos of C is 1/3. So does that help us? Well, you stare at this and you wonder, I don't know if it helps me or not. But what if I drew a line from B to D, like that? And then I told you, look at the triangle BCD. This triangle right here. And then look at that relationship. The cos of C is equal to basically 1/3. And if you remember just the basics, what is a cos? It's adjacent over hypotenuse, right? Now, if this triangle, we don't know yet, but let's say this triangle had a right angle right there. What would be the adjacent over the hypotenuse for angle C? The adjacent would be x, and the hypotenuse would be 3x. Which would be 1/3, which is exactly what it is. So that means that this angle is indeed a right angle. Therefore, angle CDB is 90 degrees. It's the only way that the cos of C can be 1/3. And therefore, if that angle is 90 degrees, that proves that this is the diameter. Why? Because I'm sure you remember, anytime you draw an angle that involves the diameter of the circle and any point on the circle like that, if an angle like that is inside the semicircle, where one point and the other point are the diameter and the third point is on the circle, that angle is always 90 degrees. So therefore that means, since that angle is 90 degrees, CB is the diameter of the circle. And that is what they were asking us to prove in this question. Prove that BC, or CB, same thing, is the diameter of the circumscribed circle. A positive integer n is called savage if the integers 1, 2, all the way to n can be partitioned into 3 sets, A, B, and C, such that the sum of the elements in each of A, B, and C is the same. A contains only odd numbers, B contains only even numbers, and C contains every multiple of 3 and possibly other numbers. Part A, show that 8 is a savage integer. So in our part A, n is equal to 8. And that means our set of numbers is 1, 2, 3, 4, all the way up till 8, like this. And we have to now partition them into 3 sets, A, B, and C. And we have to do it in a way to meet these conditions. The first condition is that the sum of the elements in each of A, B, and C are the same. So whatever numbers we put here from this group, and if we add those numbers, that sum has to be the sum here and the same as the sum there. Okay? The next condition is that I can only put odd numbers in this A, I can only put even numbers in B, and C has to contain every multiple of 3. Okay, so let's first start with C, because I think that's easiest. Every multiple of 3. So that's 3 and 6. That has to go into C. Now, like they say, and possibly other numbers, but we don't know those numbers yet. A contains only odd numbers. All right, so 1, 3 is already taken, 5, and 7. That's the only numbers that can go in A. How about B? B is only even numbers. So 2, 4, 6 is already taken, and the only other number is 8. Okay, so that's my initial partition. Is that going to work? Well, let's see. What is the sum? The sum here is 6 plus 7, which is 13. The sum here is 14. And the sum here is 9. So that obviously doesn't work. We satisfied conditions 2, 3, and 4 pretty well, but condition 1 is not satisfied because the sum in all 3 has to be the same. Okay, no problem. What is the total sum of all these numbers? If I get the total sum, that will help me. From 1 to 8, you can add them, or you can use that famous formula that I'm sure you know, adding a group of consecutive integers up until n. The sum is n times n plus 1 over 2. For 8, you don't really need to do that because it's such a small group, but let's just do it. 8 times 9, 72 divided by 2 is 36. So the sum of all the numbers from 1 to 8 is 36. They have to be divided in a way so that each of these 3 have the same sum. So this has to be divided so group A gets 12, group B gets 12, and group C gets 12. So the sum here must be 12, the sum here must be 12, and the sum here must be 12. So we have to do a little bit of mixing and matching, right? We've got to take something out. Well, the sum was 13, I've got to make it 12. So what do I take out? Well, take out the 1 and put it here. All right? How about this one, group B? The sum was 14, I want to make it 12. So what do I take out? Well, you can take out the 2 and then put it there. If you do that, let's see, what is my new sum here? 5 plus 7, which is indeed 12. My new sum, once I take out 2, 4 plus 8, which is indeed 12. And now I took that 1 and I took that 2 and I put it in here. Now the new sum would become 3 plus 6, which is 9, plus 1, 10, plus 2, 12. There you go. I've done it. So I have proven that 8 is indeed a Savage integer because I was able to meet all of these conditions. All right? So now let's move on to part B. Prove that if n is an even Savage integer, then n plus 4 over 12 is an integer. So remember, if you've got n as an integer, then you take all these numbers all the way up till n, and you have to basically divide them into 3 groups. A, B, and C, like that. And then you have to meet all the criteria. Now, we have to add up the sum first, because if you add up the sum, it makes it much easier for us. We know that each of these will be a third of the sum, like we did previously. So what is the sum? Well, it's n times n plus 1 over 2, the total sum of all the numbers from 1 until n. Now it has to be divided evenly into three groups, A, B, and C. So each of these groups will get 1/3 of this. So for example, if you remember in our previous question, the sum was 36 and each of those sets had to have 12, right? That's how we divided it. So in a very similar way, when you just have n, this n plus 1 over 2 has to be divided in 3 ways. But they tell you something very important, that n is even, right? Hope you didn't miss that. So if n is even, it's got to be of the form 2m, right? All even numbers are basically something multiplied by 2, and that something is an integer. So instead of writing this guy, I'm going to use 2m as my value for n, because they told me it's even. So it's 2m times 2m plus 1 over 2. That's my sum, my total sum of all my numbers. Okay? And this guy has to be divisible by 3. Why? Because that's the only way you're going to be able to put 1/3 in each of A, B, and C. So that is basically how we proceed with the question. This right here, we have to show that this guy is divisible by 3, yes or no? And if we do, then great, we proceed with what we have. If we don't, then it can't work. So the way we proceed is with 3 scenarios. Scenario 1, Scenario 2, and Scenario 3. We have to understand that this number n, this magical number that we are working with, it's even, right? Sure, we know that already. But it also can only have 3 possible forms. The first form is 6k. The second possible form is 6k plus 2. And the third possible form is 6k plus 4. These are the only forms that n can have. Why? Because n is even. And n, once you make it into an even number and you put it into the sum, this has to be divisible by 3. And that can only lead to n having these 3 forms. Okay? Now, each of these, one by one, we have to show whether or not this total sum is divisible by 3 or not. So let's start with the first one. When n is equal to a form such as 6k. All right, if n is indeed 6k, what is the total sum? 1, 2, 3, 4, right? The set, ... all the way till n. What is the total sum? Well, n is equal to 6k. So using our magical formula, n plus 1 times n over 2, that total sum basically becomes 6k times 6k plus 1 all over 2. Correct? Nothing fancy here so far, I hope. Now this, because it's divisible by 2, can be just written as 3k times 6k plus 1. Okay? Now, is this divisible by 3? Remember, it has to be divisible by 3. And the answer is yes, absolutely, because there's a 3 there. So this, whatever it is 3 times something, and therefore it's divisible by 3. So there you go. But we're not quite done yet. You can't just say, okay, great, let's move on. You have to at least test it out. So I'm going to test it. How am I going to test it? By giving some value for k. And let's say I use k equals 2. Any value, I mean, you can use whatever you want. Okay, if I use k equals 2, that means n becomes 12. Correct? N is 6k. So that means we've got 1, 2, 3, all the way up till 12. That's my set, right? Now, what is the sum of this? Well, by now you're an expert. It's 12 times 13 divided by 2. which is equal to 78. All right, now this 78 has to be divided into three different sets, right? A, B, and C, you remember? So each of them would get an equal amount, 78 divided by 3, which is 26, correct? Now, look at subset C and pay close attention to C. C, if you recall, only gets in numbers that are multiples of 3, right? Right here. C contains every multiple of 3 and possibly other numbers. Okay, no problem. We can create C pretty quickly here. All the multiples of 3, so 3, 6, 9, and 12. 3, 6, 9, and 12. Now, let's add up that sum. What is it? It's 9, 9, and 12, right? So that's 30. Well, we got a little bit of a problem here, right? Because the sum has to be 26. How can you get 30? It's impossible. You can't get a sum of 30 because 30 is now greater than 26, and you can't take anything out of 30. You can take things out of A and B, if you remember. I showed you that in part A, but you can't take elements out of subset C. So unfortunately, despite the fact that we did show that this was divisible by 3, n equal to 6k doesn't work. So we put a big X beside that. All right, no problem. Let's move on to n equals 6k plus 2. At this point, we have 1, 2, all the way up till n, and we want to find the total sum, right? Total sum is, of course, n times n plus 1 over 2. So if n is equal to 6k plus 2, that becomes 6k plus 2 times 6k plus 2 plus 1, which is plus 3, all divided by 2. If you expand this out, you'll get 36k squared plus 18k plus 12k plus 6 all over 2. And if you divide through by 2, you'll get 18k squared plus 15k plus 3. And this factors a 3, so we get 6k squared plus 5k plus 1. Now, is this divisible by 3? Yes, it is. All right, so that is great, but we again have to test it, just like we did. All right, no problem. Let's use k equals 2 again. It's a nice small number. Let's see what we get. So if k is equal to 2, that means n is equal to 14, right? So that means the subset of n is 1, 2, all the way up until 14, like that. So again, let's figure out the total sum. The total sum of this is 14 times 15 divided by 2, which is equal to 105. And 105 has to be divided evenly into subsets of A, B, and C, like that. And each of them gets a third, so each of them gets 35. Now let's look at subset C, because that's the one that's, I think, easiest to look at. We got to put in there every multiple of 3. So 3, 6, 9, 12 go in there. 3, 6, 9, 12. What is this sum? Well, it's 30. All right, it doesn't match, but it's okay, because remember, we can bring things from A into C. We can bring things from B into C. And if we do, we can get this number up to 35. So this is possible, since 30 is less than 35. Possible. Just like we did in part A. Go back and look at part A, how we did that. Initially it didn't work, so then we had to take something out of A, put it into C, then take something out of B, put it into C. So same scenario here. So that's good news for us. So that means that basically n is equal to 6k plus 2. That will work. So we go back and we put a big check mark right there. And we got one more word worrisome type of n that's 6k plus 4. Let's see if that works. So we've got to now figure out n is equal to 6k plus 4. Does that work or not? Okay, very similarly, we have 1, 2, 3 all the way up until n. And the sum, of course, is n times n plus 1 over 2, like that. And since n is equal to 6k plus 4, this sum becomes 6k plus 4 times 6k plus 5 all over 2. This is our total sum of all these numbers here. And if you expand that, you get 36k squared plus 54k plus 20 all over 2. And if you divide through by 2, you get 18k squared plus 27k plus 10, like that. And if you factor out a 3, you won't be able to because this is 10. But if you break that into, say, a 9 and a 1 like this, you'll be able to factor a 3 out of that. So it'll be 3, 6k squared plus 9k plus 3 plus 1. Now, look at this carefully. Is this whole thing divisible by 3? It's not, because it's 3 times something plus 1 at the end. So this is not divisible by 3. So basically what that means is that when n is equal to 6k plus 4, we can't make this work. We can't make any kind of 3 subsets that has an equal number, because this total sum must be divisible by 3 in order to do that. So we basically showed that the only way we can have this is when n is equal to 6k plus 2. Because this one didn't work. All right, so n is equal to 6k plus 2. So let's work with that. Now we have to show, hopefully by this point you might have still remembered, that n plus 4 over 12 is an integer. This is what we have to show. All right, let's see. N is equal to 6k plus 2, right? So if I plug that into here, what do I get? I get 6k plus 2 plus 4 divided by 12, which is equal to 6k plus 6 over 12, which is basically, if you divide top and bottom by 6, you get k plus 1 over 2. Correct? So now let's make a little table and see what we get here for values of k. Now, when I create this table, I will save you the pain of listening to me calculate the values every single time, and I'll just fill it out for you and come back. So I filled out the table for k equals 1, 2, all the way up to 11. And you'll notice something interesting, that when k is a odd number, such as 1 or 3, 5, and so on, this works. N plus 4 divided by 12 becomes an integer. But when k is an even number, it doesn't work. So that makes me conclude that k is odd, or must be odd. So all odd numbers are of the form 2m plus 1, right? All even numbers are of the form 2m, and if you add a 1, it becomes odd. So that basically means that our n, which was 6k plus 2, is of that form only when k is odd. So when k is, for example, 2m plus 1. So we plug that in, 6k, but k is 2m plus 1. It's an odd number. And therefore, n becomes 12m plus 6 plus 2, which is 12m plus 8. All right? And now finally, we have to show that n plus 4 over 12 is an integer. Okay, that shouldn't be a problem. N plus 4 over 12. This is the form that we concluded that n is in over a long period of time. And therefore we plug that in, 12m plus 8 plus 4 over 12. And this gives me 12m plus 12 over 12. And that basically is m plus 1. So that means that n plus 4 over 12 is equal to m plus 1. Well, m is an integer, and therefore m plus 1 is an integer. What was m? M is basically what I used to make k into an odd number. So there you go. We have proven that. Therefore, if n is savage, it is of the form n is equal to 6k plus 2, which, when k is odd, of the form k equals 2m plus 1, makes n plus 4 divided by 12, an integer, of the form m plus 1. So there you have the proof. Part C, determine all even savage integers less than 100. Let us approach this question by making a table. The first column will be n. The second column, since n is equal to 6k plus 2, I will make the second column k, and remember k is odd. And then the next one will be our set A, set B, and set C. And then after that, I will write the total sum. And then the second last one will be the common sum, which is of course just the total sum divided by 3 because there's 3 sets. And then, is this possible? Do we have success or not? So let's first fill out n. And we want less than 100, correct? All right, so, and we want even. Okay. So k is odd. So let's look at 1, 3, 5, 7, 9, 11, 13, and 15, because I think after k equals 15, we'll start getting values of n that are greater than 100. So just based on this formula right here, if k is equal to 1, this will be 8. This will be 20, this will be 32, 44, 56, 80, 68, 80, and 92. Right. And then if you make 17, it'll be greater than 100. It'll be 104, so we don't want that. We don't need that one. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities, right? Okay. All right, let's proceed. So the first one, this one actually we figured out was a savage number in part A. So possible, yes. But let's revisit it. It doesn't hurt. The total sum, if you remember, n is 8, right? So the total sum would be 8 times 9 divided by 2, which is 72. And then the common sum, of course, sorry, that's not 72, it's 36. And the common sum, of course, was 36 divided by 3, which is 12. And what I always like to do is concentrate on set C. Set C helps me the most. Now, set C has all the multiples of 3, remember. So it had 3, 6, and that's it for n equals 8, right? So this sum is a sum of 9. And since it's a sum of 9, we need to add something to it from set B and set A. Remember? And that's the only way we can get it up to 12. And if you remember, set A had a 1, a 5, a 7, like that. So we had to take the 1 out and put it here. And then set B, if you recall, was 2, 4, and 8. And we had to take the 2 out of there and put it there. So we actually proved that this works, but I wanted to sort of remind you, refresh your memory. Okay, great. We have one that they sort of gave us, but that's no big deal. I mean, definitely helps us. Now let's move on to the second one, when n is 20. Okay, a little bit longer, but let's do that. 20 times 21 divided by 2, that's the total sum. And the total sum is 210. And if the total sum is 210, you divide by 3, and you get the common sum. All right? Now again, I always got to work on set C. So a little bit longer this time, 3, 6, 9, 12, 15, and 18, correct? Right. And what's the sum of these guys here? The sum of 3 plus 6, 9, 12, 15, 18. The sum is 63. All right? So far so good, right? Because 63 is less than 70. Okay, that works because I can take something from A, put it into there, take something from B, put it into there. So it looks promising. Now let's look at set A. What's set A? A little bit longer, but it's okay. 5. I can't put 3, remember, because 3 is already there. You might wonder, like, why is he not including 3, even though 3 is an odd number? 13, 17, 19, and that's it. So what is this sum here? This sum is 73. Now remember, it's got to be 70. So that basically means I got a 3 that I have to take out of there. I've got to take something that equals 3 out of there and put it into C in order to get this 73 to become a 70. But unfortunately, there's no way of doing that. How can you take a 3 out of here? There is no 3 and there's no numbers that add up to 3. So this is not possible. Okay? I'm just going to do one more. I'm not going to go through this whole set. I'll let you guys do that on your own. But I hope you understand how this is being done. I'm going to do one more, and that's for 32. All right, so here we go. 32. First and foremost, what's my total sum? I've got 32 times 33 all over 2, and that total sum is 528. All right, and then divide by 3, and therefore each common sum has to be 176. So now let's start with set C. So we got 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. And the sum there of all those numbers is 165. All right. Is that okay for now? Yeah, it's okay. It's less than 176. So we can add something to it from set A or set B like we've done before. So now let's list set A. And set A, that sum is 181. All right, but we want it to be 176, so I've got to take 5 out of here. Can I do that? I sure can. I can just take out this 5 right there. And then this will drop down to 176. And this will go up to 170. Okay, if I take a 5 out of there and add it to here. All right, we're not quite done though because we've got to look at set B. So here's set B. That sum is 182. Okay, I got to make it 176. So how do I do that? I've got to take out 6. Is that possible? Sure. I can take out the 2 and the 4 and put those guys over here. That would make this sum go down to 176. It would make this sum go up to 176, and we are set. So therefore, this is a big yes right here. All right, so now we've got 2 savage numbers. And very similarly, you do the exact same process for 44, 56, 68, 80, and 92, okay? And I'll let you guys do that because I know that's the most fun that you could possibly ever have. And and I'll even help you out here. I'll put in the total sums and the common sums. All right, so now we're really interested in yes or no, basically, this column right here. Okay, this one, 44, is a yes. This one, 56, is a no. 68 is a yes. 80 is a yes, and 92 is a no. So the only ones in this list that are savage are 8, 32, 44, 68, and 80. All right? So I'm confident that if you follow this system, you can fill out the rest of the table all here, and you'll be able to get the same results that I have listed here. So that takes care of number 10.